Okay. Okay, let's get started. Okay. Yeah, I was looking at the NBA games. I mean, do you guys like watch NBA games? No? Okay. Yeah, I mean, I don't do much exercise, but I love watching like a lot of different sports games. Like, for example, NBA games. Like today, Lakers is playing with like Golden State Warriors. I think like it's interesting to see like LeBron James and Steve Curry playing each other. I think like probably you don't see that anymore. Like in the future, maybe next year, I think LeBron James will retire. Okay, so this is perhaps his last dance. Okay, yeah. So well, anyway, yeah. So come back to this autocorrelation. So first, like, what does that mean? Autocorrelation. Okay. You guys know like what the auto means here. Okay. I mean, for example, like auto, you see a lot of English words that start with auto, right? For example, like automobile, like anything else? Automatic. Okay. The prefix auto, okay, actually stands for self. Okay, self. Okay, so for example, like automatic. Okay, matic is like a mechanism, kinetic. Okay, so self mechanism. So it's you do something like something happen like by itself. Okay, and automobile. Okay, same thing. Mobile is something that move, right? So automobile, self move. So like the car can move by itself, right? So auto actually is a prefix that stands for self. So autocorrelation is self-correlation. Okay? You guys know correlation, right? Correlation is not a new term, right? The autocorrelation is new, but I mean, once you know the auto means self, the autocorrelation should not be too difficult to understand by you guys. Okay? So given a series, given a time series data, okay, you can compute the autocorrelation by something like this. Okay, so for example, you see there's here we have a time series data. Okay, and this ACF means autocorrelation. Okay, this 1 means k equal to 1. Remember like a previous essay, like you can compare, okay, with the itself, okay, with the trend values, k step ahead. Okay, so this k is is the what appear in the parentheses. Okay, so this 1, it just means like you move this chain 1 step to the right. Sorry, it should be 1 step to the left because you look ahead. Okay, 1 step to the left. Okay, and then, okay, you try to, because you move, if it's like let me draw something that's more dramatic. Okay, say if you have something like this. you move this thing one step to the left, what you are going to get is something like this, right? Right? So for each x value, you now has 2 points, right? You have this point and this point, right? Right? For each given x value, you have 2 points, right? Because you have 2 points at each given value, you are able to compute their correlations. I mean, if you want to calculate correlation, you need to have 2 values, right? So you are calculating the correlation of the y of these 2 sets of y values. Okay, for every every x value. Okay, so this is like if you move this one step to the left, then your k value is 1, and then for example in this example, your ACF1 is 0.96. If you remember like how we calculate correlation, 0.96 is quite high, right? Okay, the correlation normally is in between -1 to +1, right? If something is higher than 0.9, that's already very, very high correlation. So this is 0.96. That's darn high correlation there. Okay, but you can obviously imagine if it's a time series, when you increase the k, in other words, if you try to move this chain more to the left and then calculate the correlation, when you increase the k, the correlation will reduce, right? The correlation will naturally reduce. So you can see when k is when k is 5, the correlation reduced from 0.96 to 0.75, right? And if you move like 10 steps ahead, the correlation reduced to 0.55. Okay, so this lag, as I said, this represents the value of k. Okay, and you will naturally see such a decrease of the autocorrelation. Okay, so what does autocorrelation stand for? It stands for like how much dependency this time series data has. Okay, from the previous location to the next one. Okay, so for example, if I'm here, okay, for this current step, if I move next, we know like because it's a Markov chain, right? It's a Markov process. So the current step influence where you are at for the next step. That's nature, right? That's nature. But if the k is larger than 1, the autocorrelation value should reduce quickly, right? Should reduce quickly. If it's a good Markov chain, okay, if it's a good Markov chain, then it should only dependent to the previous step, not to the step like more than one step in the past, right? The lower the value of the autocorrelation indicates that the more information you can draw from this time series data. No, information theory-wise. Okay, information theory-wise. So, the autocorrelation can be computed for any lag of interest. But for our applications, okay, we typically interest in lags from around 1 to 20 also, okay, because if the K value is too big, as I said, like, it reduces quickly, right? If you already consider, I'm sorry, if you already consider like K to be higher than 20, like, I mean, pretty much all kinds of time series data will have very low autocorrelation anyway. Okay, so it doesn't, we only consider from 1 to 20. Okay, something like this. Okay, so you can see, for example, this one, okay, we care more from here to here. For something like lags that are larger than 20, obviously it reduces naturally, but we don't care that much. Not to mention this one, okay, this is also called autocorrelation, so up to 20. So you can see that, okay, if you ask me, for example, okay, remember I told you, like, you know, for representativeness, okay, there are two ways to decide how representative, like, representativeness your chain has. Like one is like the upper left figure that shows like if your chains mix well or not. I mean, if you look at this one, it looks to us that it mixes pretty well. I mean, if you only look at the upper left one, I mean, to be honest, I mean, it's, you know, if you look at this, I mean, more carefully, you will still feel like they don't mix so well. But it's hard to say, right? Because it's a visual result. So visual inspection is easily misleading because of the, you know, it's more subjective. Okay, so probably some people think, oh, this is like this mix pretty well. The chains are mixed pretty well. Some people will think, some students will say, oh, this looks like it's I mean, still they do not mix so well. Because if it's like this, obviously they don't mix well, right? This one is obvious. I mean, nobody will say they mix well. But this one is hard to say, right? Some people may say, yes, they mix very well. Some people will say, well, they don't mix so well, okay? So sometimes it's hard to say, okay? I mean, but the other clue is to look at the statistical values. For example, like autocorrelation. Okay, you can obviously see that, you know, even at around 20, okay, the autocorrelation for these chains are still higher than 0.4, right? So it doesn't really, it's really not that good. Okay, you are looking at the autocorrelation that's like much lower than 0.4 when your lag is 20. You should see this one reduce, okay, I mean, become very low very quickly. Okay, if it's not a case, then it just represents your chains are not mixing very well. Okay, or the chains are not representative enough to your posterior distribution. Okay, and so yeah, so okay, So we would like to, some measure of how much independent information there is in autocorrelated chains. In particular, we can ask what would be the sample size of a completely non-autocorrelated chain that yielded the same information. This is like the definition of the effective squared, how we define the effective sample size, the ESS. It's defined as n. This n represents like the number of samples that you draw from. Maybe for example, like we draw 2,000, right? Okay, but in a different textbook we draw like 10,000. But you get an idea that n represents like a number of samples, like you draw, or by using the sampling algorithm. Okay, you can obviously set it like by yourself. But this n is divided by this parenthesis 1 plus 2 times summation k equal to 1 to infinite ACFK. Okay, first, because this autocorrelation is almost guaranteed to be greater than 0. Okay, so this value is not likely to be negative. Okay, so you can imagine this 1 plus something. This denominator, this is greater or equal to 1, right? Okay, so in other words, like your n, okay, even though you draw like say like 10,000, maybe at the end the effective sample size is not going to be that high. Okay, if you want your chains to be representative, you make sure this ESS value is large enough. Okay, not the number, not this n, okay, but the ESS value. Okay, but as I said, the better the sampling algorithm that you use, the more likely this value will be smaller. Okay, and you may say, well, this is k from 1 to infinite. How can we calculate that value? Because, well, this is an infinite series. And it looks like it's difficult to calculate, right? But in practice, this infinite sum, okay, you don't need to calculate like from k to 1 equal to 1 to infinity. As long as you get a term, okay, that is or smaller than 0.05, you can stop. Because it should be, when you stop at this value, okay, you add like from k equal to 1 to this k value that makes this ACFK smaller than 0.05. This summation should be representative enough for you to calculate this ESS. Okay, so come back to this one. Look at here, ESS equal to 605.8. It was indicated at the upper right corner of the upper right figure, the ESS. So this one actually, how many samples did we draw? Okay, we actually, the first 500 is used for tuning. So we actually, did not account for the first 500. But we, from 501 to 10,000, we actually, each chain has, 9,500, right? So it's pretty long chain, right? But such a long chain, their ESS is only 605. That's due to the fact that we have a relatively high autocorrelation. Okay, in other words, like this chain, okay, they didn't provide like enough independent information in the chain. Okay, that, as I said, this is affected by mostly the sampling technique. And because this example, we use like a Metropolis algorithm. So Metropolis algorithm, as I say, is like the first algorithm like in this sampling technique. Okay, so it is a relatively simple, naive sampling technique. That's why, okay, it's not very effective, as you can see. Okay, yeah, I mean, for the other type of sampling technique, for example, like Gibbs, or like the one that we use, I mean, for our textbook, okay, they are more advanced sampling techniques. So normally the number of samples you draw will be closer to the ESS value. Okay, so for example, sometimes you may even see like you know, this ESS value to be larger than n. Why is that? It's because like you know, yeah, it's not impossible. You sometimes can find that, can see that. I mean, where is it? Okay, because you can remember like it's defined something like this, right? So I mean, it's autocorrelation, right? So correlation could be negative, right? It could be negative, but most of the time it's positive. I mean, when it comes to autocorrelation, but it doesn't guarantee it could, I mean, it's not negative. So yeah, I mean when the SFK is negative, I mean it could impact the ESS to be larger than the number of samples. It's possible, but not very likely. Okay, not very likely. I mean, let me go back to. Let me. Sorry. I just want to show you the. Yeah. Yeah. So this. The reason, you see, we have this kernel function, okay, and this you know the chain, okay. So this one is the upper left corner figure. This one is the lower right figure. I mean, yeah, I mean these two figures are the most important ones. I mean, and what I was trying to tell you is this one. Okay, this EFFN is the effective sample size. And remember how many samples did we draw? I mean I just arbitrarily pick this one, okay? So this one is like where is it? Where they show, well, we didn't shoot. Oh yeah, here. You can see it's about 1,000, right? we draw like about 1,000 samples, right? Okay, and so it's, you know, it's quite effective, right? I mean, close to 1,000. I'm not saying that it's 1,000, okay, but it's close enough, right? I mean, it's the effective sample size is like more than 80% of the sample, right? So it's pretty nice. It's pretty nice already, and that's because like the sampling tech algorithm that was used in our textbook. Let me use another example. So this one we draw like 2,000 samples, right? And do we have this? Yeah, you can see sometimes it can even be larger than 2,000. Not very likely, but sometimes it happens, especially in some simple cases. Because this is like, remember this case is very simple. We only have one outlier, something like that. If you still remember the case, this example. So the reason, okay, I want to talk about this part is to talk about, you know, because at that time we, you know, the mean standard deviation, the MC error. This one is like you don't need to worry about that. This is for like Markov chain error, okay? But these two fields are pretty much easy to understand, okay? It just represent like the range of your 94% HPD. But this one is important because it tells you like how representative your chain is, okay? So there are so many of these like well, yeah, you can find, I mean, a lot of this. This one we generate 2,000 samples, and the result. Do we have the result? Well, we didn't put the summary here. Right here. Yeah, we generate 2,000, but this one. Yeah, this one is, yeah, it's because of the relatively simple case. I mean, because this case was generated by us, but a lot, I mean, of this is also due to like the effectiveness of the sampling techniques, okay? So I just want to tell you the meaning of that field, okay? So, oops, shoot. Yeah. So ESS, okay. So each chain, okay, basically, I mean, has like a 9,500, n equal to 9,500. So yielding like a, oh, I forgot to mention, yeah, this is actually like a, you have to add them up. So, so because we have like multiple chains. So 9,500, so total will be 28,500. But the autocorrelation is high, so that ESS is only 605. Okay, so same thing apply for the previous ones. Okay, I forgot to add them up. No wonder it's like easily over like 2,000. Yeah, because in the textbook example we have like 3 chains, right? So 2,000 actually end up having like 6,000 samples. So 6,000 samples. I mean, remember like we saw like ESS to be like 5,000 something, right? So that's like reasonable, okay? So how big should the ESS be for accurate and stable? Oh, by the way, I forgot to mention, okay?